All right, silly people, here's the situation. We need to find the eigenfrequencies of oscillations for this configuration of springs and charged masses. Um, you can see in my really awesome drawing that there are three springs in the problem, each with the same spring constant k, also each with the same length a. Um, and each of the charged masses have charge q and mass m. Um, for the purposes of the problem, I have defined the position of the first mass, um, that is eta 1 is equal to x1 plus a, um, and the position of the second mass as x2 plus 2a. Um, that way we can get some nice cancellation in our potential terms. And then going from left to right, I've called the springs S1, S2, and S3. Um, so to find eigenfrequencies, actually we don't even have to find the eigenfrequencies. All the problem says is that we need to set up the secular equation to find the eigenfrequencies. And that secular equation is this, the determinant of the potential energy matrix minus omega squared times the kinetic energy matrix is 0. That's what we're solving. What actually are those tensors? Those are just, okay, so the potential energy matrix is actually just a Jacobian of the potential. So del squared V del eta I del eta J. Yep. And so the kinetic energy matrix is just going to be the mass of the two particles times the identity tensor. Um, cool. So we need to find the potential. That's what the problem is, pretty much. We need to find the potential energy of this situation. There's going to be three spring potentials. One for the first spring, which I'm going to call V1s or VS1, and then there's going to be one for VS2, VS3. There's going to be an electric term because we have charged particles. So for the first one, it's just your regular old spring potential, k over 2 times the position of the mass minus its equilibrium position squared. See what I did there with the coordinate definitions? Those a's inside the squared term cancel out. And so we just have k over 2 x1 squared. Not too bad. Same thing for spring 3. It's just a normal old spring potential, where now we're looking at the second mass there minus 2a. So that's going to be k over 2 x2 squared. The one in the middle is going to be k over 2 on the inside. Both sides of this spring are allowed to oscillate, so the position is considering both sides, so it's the 2a side minus the 1a side minus the equilibrium positions of both. So it's going to be minus 2a plus a. Hopefully you can see that all of those a terms cancel out. But what we're left with is k over 2 x2 minus x1 squared. Not as simple as the last bit we did, but we can go ahead and expand that just by squaring this stuff inside the parentheses. And now this is important. So this is under a theory of small oscillations. So we don't really have to um, deal with this term because x1 and x2 are so small as compared to x1 and x2 that we can cancel it out, not even think about it for the rest of the problem. And we're going to be doing that a lot, this problem. So the potential due to the electric charge of the masses is going to be your normal Coulomb potential. It's going to be Q times 4 pi epsilon, or divided by 4 pi epsilon naught, divided by the distance between the two points, the two masses, which we've already determined is just x2 minus x1 in the last bit. Adding all the potential terms together, it's k over 2 for all of them, and then we have an x1 squared, an x2 squared, and another x1 squared and another x2 squared, and also the electric term. Great. I'm gonna simplify. I'm gonna collect terms within the first term to say just that, and then move this guy down here. Right. That's the potential energy. Boom, bam. Now, how do we get that lovely potential energy matrix Vij? Let's just start taking partial derivatives. dv dx1, that's going to be 2kx1 plus q over 4 pi epsilon naught. Then we'll have 1 over x2 minus x1 squared on the bottom. We've already determined that x2 minus x1 squared, whenever you expand it, has a term that goes away. So I'm going to go ahead and do that. X1 squared plus x2 squared. Awesome. Now let's take the second derivative of that with respect to x1. Now we just have 2k there. We still have that stuff, but now we have 2x1, and now it's minus, actually, minus 2x1. On the bottom, it's x1 squared plus x2 squared squared. Which we can do the same trick before of expanding that and excluding the cross term. And we'll have 1 over x1 fourth plus x2 fourth. Right. Now, just do the same process again. Well, actually, let's look at the first crossed term. So del squared v del x1 del x2. So we're taking the partial derivative of this stuff up here with respect to x2. The first term goes away. The electric potential term, though, minus sign. I'll skip the nonsense. We have fourth terms on the bottom and a 2x2 term up there. Right. Now, all we're missing is the second derivative on the other side. So let's do single derivative of the potential with respect to x2. it's going to look pretty much the same as the first derivative with respect to x1, except now this is a minus sign. 4 pi epsilon naught 1 over x1 squared plus x2 squared. Cool, now the second derivative with respect to x2, it's just 2k minus, now it's plus up here, plus 4 pi epsilon naught. And then up here it's 2x2. On the bottom, x1 to the fourth plus x2 to the fourth. And then the cross term, after doing x2, you do x1. And you say 2k, actually no 2k, just the q over 4 pi epsilon, not 2x1 up top. It's not a minus sign, it's a plus sign. Then x1 fourth plus x2 fourth on the bottom. So that's all of the terms, actually. So we can write the whole matrix, Vij. I am just going to copy everything down and move it, though. That one. And this one. Both of the diagonal terms have factors of 2k. But the cross terms do not, which is funny. Where's the other one? There it is. All right, there's your potential energy matrix. Boom, bam, done. Done, not really. We still need to set up the secular equation, but that's not too hard. Because remember, it's just the determinant of Vij minus omega squared. It's going to be omega squared m del ij, which was what we determined was the kinetic energy tensor. So it's pretty much just going to be this same stuff again, but the diagonal terms are going to have a minus omega squared m. So I am just going to copy that over. Copy, paste. And then I'll give the terms on the left some room so I can write my minus omega squared m, minus omega squared m. You set that equal to 0, and you can solve for your eigenfrequencies. The problem doesn't ask you to solve for the eigenfrequencies, it just says to set it up. That's because this one is bitch to do, actually. And I can say with a fact that I don't enjoy doing it, so I'm not going to do it. I'll just leave it as Goldstein intended.